everyone, my name is Nathaniel and I hope you all are keeping safe during this pandemic. Today during this presentation, I'm going to be talking to you about a revolutionary new technique called LEAPER. Through this presentation, I'm going to try proving to you why I deem LEAPER the innovation of the decade. LEAPER was first discovered and created in 2019, and it works at the RNA level. We'll get into all those specifics later, but before we can understand why LEAPER was needed to be created, we have to understand the limitations of the other techniques. So why don't we delve into that first? First, we're going to start with DNA techniques, DNA editing techniques. You may ask me why. Well, a lot of these RNA editing techniques actually are derivatives or were derived from a lot of DNA editing techniques. So let's look at the three big ones that we generally hear about most often. ZFNs, TALENs, and CRISPR-Cas9. Without getting into too many details of how these things work, because I'm sure you guys are sick of hearing how these things work, let's just look at the limitations of these DNA editing techniques. First of all, the specificity limitation of it, the cost of these things, temporal regulation of a lot of these systems, the introductory method, and what I mean by that is, especially for CRISPR-Cas9, is that the Cas9 molecule is very big and you need a guide RNA. In order to get it into the cells, you need a very effective introductory method or vesicle method. So that's another limitation of it. I said cost before, and the one that's also very big is off-target effects, especially with the DNA techniques. But ultimately, what we have to understand about DNA editing techniques is that anything we do with the DNA is permanent. We edit, we change a base pair, it is permanent for the rest of that cell's life and probably the rest of the organism's life. So with these limitations in mind, and we can see how much of a detriment it can be to a patient receiving this kinds of therapy. But the issue with DNA editing techniques is that we know a lot of diseases are actually misexpression of enzymes, overexpression of proteins, and basically work at an RNA level. So why not use techniques that are needed or work at the RNA level, which is what we get to now. We look at RNA techniques and their limitations. So the major RNA techniques that we see and we hear about is the RNAi and miRNA. Again, I won't get into details how these things work, but we know that they're used to regulate our natural levels of RNA within our system. But the one that has been created was the CRISPR-Cas13 system. The CRISPR-Cas13 system works very similar to CRISPR-Cas9, but it works at the RNA level. The big problem with CRISPR-Cas13 is that it is very non-specific, unlike CRISPR-Cas13. So now let's look at these three and let's look at the major limitations that we have of all three. The first limitation that we have with all three is that they work at the RNA level, but very non-specifically. You get unwanted immune responses. So what does that mean? Very preliminary research has shown that using specifically the Cas13 molecule, you get an increase in autoimmune response, which is a big problem for any of you that took immunology. The big one that I mentioned before with Cas9 is that Cas13, you have a transport problem. Because it is such a big molecule, Cas13 is such a big molecule, and it needs a guide RNA, you need a very specific transport molecule, and a very big one in this case. It's because it's a very big cargo. Any kind of RNA editing technique uses and utilizes a molecule called ADAR1. ADAR1 is naturally found in the cell at very specific amounts. But using these techniques actually increases ADAR1 within the cell. This is a big problem because a lot of research has shown that this is actually oncogenic. The big problem that I said before is the lack of specificity, so you have off-target effects, decreasing the amount of maybe needed RNA within the cell. And also a very interesting study that was done showed that the Cas13 molecule actually binds to and inhibits P53. P53 is our main tumor suppressor, so you can see by inhibiting P53, we could actually have an increase in a lot of cancers. So by using Cas13 and a lot of RNA editing techniques as a therapeutic for certain diseases, but at the same time, we're increasing our chance of cancer, that's a big problem. So with these limitations in mind, researchers were forced to find a new technique that didn't have as many limitations, but had a lot of these pros that are needed with RNA editing. Thus, we come to my big friend LEAPER. LEAPER stands for Leveraging Endogenesis, ADAR for Programmable Editing on RNA. It's a mouthful, which is why they call it LEAPER. Again, I won't get into the specifics of exactly how LEAPER works. We'll just look at the limitations that we mentioned before and how LEAPER is better. So LEAPER only uses something called an AR-RNA, which is an adequate length RNA. It is this very small piece of RNA that can be transported via a viral vector or a plasmid. So the carrying capacity is very, very small. And that's the only thing LEAPER needs, is this very specific AR-RNA. It uses the cell's regular levels of ADAR1 in order to correct, edit, and delete certain RNAs. This is a big pro because it doesn't actually increase the ADAR1 molecule levels within the cell, thus lowering the chance of cancers and the oncogenic effect. Since AR-RNA, that small molecule that LEAPER uses, is small, as I said, it actually doesn't create an immune response, which is a huge plus than from the other RNA editing techniques that we saw. It is very, very inexpensive to create because you're only using this very small RNA molecule, and it's very specific. So you have a very low cost and a very high specificity and almost virtually no off-target effects because it is specific to a certain RNA molecule. So as we can see, all the limitations from the other editing techniques that we saw is actually the advantages of using LEAPER. Now that I've told you why I deem LEAPER as the innovation of the decade, because of all these positives and very little negatives that it has, I like to look at real-life examples. So why don't we do that? Hurler syndrome. Hurler syndrome is is actually not very common, but it is a very detrimental disease to babies being born. There was a study in China where they had used the CRISPR-Cas9 system to edit some of these patients' genomes, and the other study the other group was using LEAPER as a therapeutic. What they found was that CRISPR-Cas9, as we know, has a lot of off-target effects, and these kids were actually worse off using CRISPR-Cas9. Hurler syndrome is a defect in one enzyme. The enzyme is called the mucopolysaccharidoses type 1 enzyme. So it only makes sense to use an RNA editing technique because you can edit this enzyme to create a working enzyme without permanently changing the DNA. And that's exactly what these researchers did. They used LEAPER as a therapeutic in order to edit the enzyme in order to make a functioning enzyme, a proper functioning enzyme. And what they found was that the kids that were born with Hurler syndrome, they saw an 80% decrease in their symptoms, which is huge. There was no increase in cancer, there was no autoimmune responses detected, and there was actually very limited off-target effects seen. Again, these kids are still under trial and still under test, but from what the research shows initially is that LEAPER was highly advantageous over CRISPR-Cas9 and even over CRISPR-Cas13. Now let's go one step further and look at another syndrome that is very similar called Hunter syndrome. Hunter syndrome is just a lot more advanced than Hurler syndrome, and it just spells disaster because these children generally don't last very long. The same procedure was done, but in this case they used CRISPR-Cas13. And what they found was that CRISPR-Cas13 had the exact same effects as CRISPR-Cas9. They had a lot of autoimmune issues, they had a lot of off-target effects and non-specificity. But when used LEAPER, these kids actually saw a reduction of 75% of their symptoms, which is huge. So what they found was that using LEAPER as an RNA editing techniques was specific, they didn't have many off-target effects, and they were able to reduce a lot of these kids' symptoms that they were having issues with, and it actually promoted a longer life in a lot of these kids. Now looking at a very pertinent issue as cancer, which is to our lives, we see that in a preliminary study that I found was that using AR-RNA, and LEAPER in this case, it actually increased the expression of P53. By increasing the expression of P53, which is our main tumor suppressor, we're able to basically reduce the amount of cancers that we see. So using LEAPER not only is very specific, can help us with many diseases, but also decreases the amount of cancers that we have, or at least help us combat a lot of cancers that we see in our daily lives. So that's a huge advantage, which is again another reason why I deem this the innovation of the decade. So in conclusion, as a wrap-up, we talked about what LEAPER is. I talked about how it is better than a lot of RNA editing techniques. I showed you real-life examples where LEAPER was used to help children with certain symptoms. And through all of this, I hope I've proven to you why I deem LEAPER as the innovation of the decade. I can only see LEAPER getting better from this point, more specific, used and utilized in a lot more contexts. So I just can't wait to see how LEAPER is going to be used in the future. Maybe the researchers are right. It's going to be better than CRISPR-Cas13 and CRISPR-Cas9. We'll see. These are the citations that I looked at when researching my topic for LEAPER. If you're interested, you can definitely go see. I hope you all are keeping safe during this time and hope to see you all soon. Thank you.